The United States alone consumes over 7 billion liters of fuel daily, powering 800 million vehicles worldwide. But have you ever wondered how that fuel gets from deep underground to your gas tank? This is the complete story of Petroleum, from the massive Texas oil fields where companies like Occidental drill one new well every day, to the sprawling refineries where crude oil is heated to 370 degrees Celsius and transformed into the clear, powerful fuel that makes modern life possible. What if I told you that the fuel in your car was once a living creature millions of years ago? It's a fascinating transformation that begins deep beneath the ocean floor. When ancient plants, animals, and microorganisms died in prehistoric seas, they sank to the bottom, gradually becoming buried under layers of sediment. Under intense heat and pressure, these remains underwent a remarkable chemical metamorphosis called catagenesis. This process didn't happen overnight. It took approximately 250 million years for these organic materials to transform into the hydrocarbon-rich substance we know as crude oil. Think about that time frame, 250 million years to create what our modern society consumes in mere decades. This stark contrast highlights our relationship with this finite resource. The oil powering your morning commute represents an ancient energy bank that took geological eras to deposit, but is being withdrawn at an unprecedented rate. Before we can use this sticky, smelly black liquid, the primary raw material for gasoline, we first need to find it. Modern oil exploration has evolved dramatically since the industry's Texas beginnings in 1894. The real boom started in 1901, but today's methods bear little resemblance to those early days. Finding oil beneath the Earth's surface requires sophisticated detection methods. Geologists now employ advanced seismic technology that works by generating sound waves that penetrate deep underground. These waves bounce off different rock layers and return to the surface, where sensitive instruments record them. By analyzing the time these waves take to return, experts create intricate three-dimensional maps revealing potential oil and gas deposits. When examining these maps, geologists look for specific geological formations that typically trap oil. They search for anticlines, upward-folding rock layers, salt domes, and fault traps, structures that prevent oil from migrating further upward. They also identify porous reservoir rocks like sandstone or limestone that can hold oil, topped by impermeable cap rocks that seal it in place. Despite these technological advances, finding oil remains a calculated gamble. The subsurface geology is notoriously complex, with unexpected variations that can turn a promising prospect into a dry hole. Yet the scale of operations in places like Texas demonstrates both the economic incentive and industrial commitment to this pursuit. The sheer magnitude of drilling operations in Texas oil fields is staggering. Each month, over 2,000 new wells puncture the Texas landscape, collectively extracting more than 900,000 barrels of crude oil daily. This continuous drilling is necessary to maintain production levels as existing wells gradually deplete. Major players like Occidental Petroleum exemplify this relentless pace. To sustain their production targets, they drill approximately one new well every single day. This constant activity represents billions in investment and thousands of jobs, all dedicated to extracting a resource that lies thousands of meters beneath our feet. The journey to reach these deeply buried deposits is an engineering marvel. Modern drills must penetrate up to 4,000 meters, nearly 2.5 miles, through various rock layers to reach oil-bearing formations. At these depths, drilling teams encounter extreme pressures and temperatures, while navigating through different geological strata with specialized drill bits and mud systems that lubricate and cool the equipment. Once a promising location is identified, engineers deploy seismicians that provide astonishingly detailed 3D maps of underground formations. These technological wonders allow them to visualize oil deposits with remarkable precision, identifying the optimal drilling points and potential extraction challenges before a single drill bit touches the ground. While the seismic imaging technology pinpoints exactly where our crude oil resides, extracting it is merely the first challenge overcome. The viscous black liquid emerging from the wellhead bears almost no resemblance to the clear fuel it will eventually become. And between these two states lies a perilous journey, spanning thousands of kilometers through a complex web of pipelines few ever witness. This extracted crude oil, thick, sticky, and almost tar-like in consistency, must now travel approximately 1,000 kilometers to reach its destination. The journey connects two critical points in petroleum's life cycle: the extraction site where it emerges from the earth and the refinery where transformation occurs. Without this crucial transportation link, all the sophisticated extraction technology would be meaningless. The logistics of moving millions of barrels of highly flammable crude oil daily presents extraordinary challenges. A single pipeline rupture can release thousands of barrels into surrounding ecosystems within minutes, potentially devastating local environments. These concerns necessitate stringent safety protocols throughout the transportation network, with constant monitoring for potential weakness or damage points. Pipeline systems form the silent arteries of our energy infrastructure, efficiently moving crude oil across vast distances through an intricate network that operates largely unseen. These underground pathways consist of specialized pipes designed to withstand tremendous pressure while carrying volatile materials. At regular intervals along these routes, pumping stations maintain the necessary pressure to keep the crude flowing smoothly toward its destination. These pumping facilities are engineering marvels in their own right, using precisely calibrated systems to maintain optimal pressure throughout the network. Too little pressure and the thick crude stalls, too much and pipes risk catastrophic failure. Engineers monitor these systems around the clock, making minute adjustments to accommodate changing volumes, viscosity variations, and environmental conditions that might affect flow rates. After its long journey, our barrel of crude finally arrives at its destination, America's largest oil refinery. This massive industrial complex spans an impressive 10 square kilometers and processes an astounding 562,000 barrels of crude oil every single day. The sheer scale of this operation becomes even more apparent when considering the 4,000 workers employed here, who collectively use over 1 million ear protectors annually just to protect themselves from the constant industrial noise. Before any processing begins, each incoming batch of crude undergoes rigorous quality assessment. Laboratory technicians analyze samples to determine the oil's specific composition, which varies significantly depending on its geological origin. These tests reveal crucial information about the hydrocarbon mix, sulfur content, and other properties that will determine exactly how the refinery processes this particular crude. The results of these assessments directly influence how engineers will approach the refining process. Different crude compositions require different treatments, temperatures, and catalysts to maximize the yield of valuable products. Based on these initial findings, technicians prepare for the transformation process by setting parameters for the coming operations. As our barrel prepares to enter the refining process, it faces its most dramatic transformation yet. The refinery will heat this thick black liquid to temperatures exceeding 370 degrees Celsius, initiating the separation process that turns raw crude into everything from aviation fuel to the building blocks of plastics. This extreme heating marks the beginning of fractional distillation, where different hydrocarbon compounds will separate based on their unique boiling points. The engineering challenges overcome to reach this point are remarkable. Consider that the oil extraction process required drilling through kilometers of solid rock, navigating complex geological formations, and bringing up material from depths few human-made objects ever reach. The sophisticated drilling technologies that make this possible represent centuries of innovation in material science, engineering, and geology. Option 2 from the Curiosity Gap options serves as the best inspiration, but I'll enhance it further to create an engaging opening paragraph for this section. The sophisticated engineering that brought our barrel of crude oil to the refinery pales in comparison to the chemical wizardry about to unfold. Inside these massive industrial complexes, crude oil undergoes a remarkable metamorphosis at temperatures exceeding 370 degrees Celsius, hot enough to liquefy zinc. This extreme heat initiates a cascade of precise separations that transform a single substance into dozens of distinct products, all while operators maintain vigilant control over processes where the margin between efficient production and catastrophic failure is measured in mere degrees. This critical heating stage represents the beginning of the refinery's most impressive feat: fractional distillation. As crude oil reaches these blistering temperatures, it doesn't simply boil, it vaporizes into a complex mixture of hydrocarbon molecules. Each of these molecules, distinguished by their unique carbon chain lengths, will soon find their proper place in the production hierarchy. The heart of this separation process occurs within towering distillation columns, massive metal structures where physics and chemistry work in harmony. As the superheated vapor rises through the column, a fascinating natural sorting begins. The heavier hydrocarbon molecules with their longer carbon chains condense first at the lower, warmer sections of the tower. Meanwhile, lighter molecules with fewer carbon atoms continue their upward journey, only condensing when they reach cooler heights that match their specific boiling points. This elegant separation creates a natural stratification within the tower. At the bottom, the heaviest residuals settle, thick, tar-like substances destined for asphalt production or further processing. Moving upward through the column, we find increasingly lighter products. Heavy fuel oils give way to diesel, then kerosene, followed by gasoline components, and finally at the tower's summit, the lightest gases like propane and butane. The precision of this separation process yields remarkably consistent output ratios. From every 191 liters of crude oil that enters the system, the refinery extracts approximately 88 liters of gasoline, nearly half the original volume. The remaining output includes 48 liters of diesel fuel, 26 liters of kerosene, crucial for jet fuel, almost 7 liters of propane, and 32 liters dedicated to other essential products ranging from lubricants to the building blocks of plastics. Quality control represents another critical dimension of the refining process. Take gasoline, for instance. Its performance characteristics must meet exacting standards before reaching your vehicle. Specialized testing engines evaluate the fuel's resistance to knocking, a potentially damaging condition where fuel ignites prematurely in an engine's cylinder. These laboratory tests provide immediate feedback to refinery operations, allowing technicians to adjust formulations when necessary and ensure consistent quality across millions of liters of production daily. The journey from distillation tower to gas pump requires another layer of precise handling. After separation and quality testing, gasoline flows through underground pipelines to nearby terminals. There, tanker trucks undergo a carefully choreographed loading process. Each truck must be grounded with a special cable to prevent static electricity. A small spark could ignite fuel vapors with devastating consequences. Additional safety systems include overfill protection sensors and vapor recovery pipes that capture emissions, preventing both waste and atmospheric pollution. The scale of this distribution system is staggering. Approximately 4 million liters of gasoline alone leave the refinery daily, traveling through a complex network of pipelines, terminals, and finally, tanker trucks bound for thousands of gas stations. This intricate delivery system operates continuously, ensuring fuel availability whenever consumers need it. What we've witnessed is not simply a fuel-making process, but the transformation of an ancient resource into the backbone of modern civilization. Beyond powering our vehicles, crude oil silently permeates every corner of our lives through plastics, tires, cosmetics, pharmaceuticals, and countless other products we depend on daily. Yet this versatility comes with responsibility. As we extract billions of liters of this finite resource daily, we're consuming what took nature eons to create. Understanding this intricate journey, from underground deposits to refined products, helps us recognize petroleum's true value, while highlighting why developing sustainable alternatives isn't just environmentally sound. It's essential for our continued progress in a world with diminishing natural resources.